So we have been talking about all these large-scale balances happily ignoring friction. Obviously, friction cannot be ignored for too long near the boundaries in the boundary layer or for the ocean where the winds are dragging the surface essentially by friction, totally by friction. You cannot ignore friction anymore, right? So we create a simple analogy to the effects of Coriolis but with friction, and look at a balance between pressure gradient and Coriolis and friction to say that flow is still to the right of friction in many of these cases. So these are called subgeostrophic flow. Ekman layer is the term, comes from Walfrid Ekman, was the first one to derive the relation in the ocean about the winds dragging the ocean surface, creating currents, Coriolis pushing the currents to the right, creating transport perpendicular to the direction of the winds, and so on. His advisor Nansen had asked him to go and figure out why icebergs were drifting at an angle to the winds. So he was a smart graduate student, Ekman, sat down and wrote a few equations and showed that you get something like that we will see later on called the Ekman spiral in the ocean. Okay, long story short, going back to our equation, du dt plus 1 over rho grad p plus grad phi equals minus 2 omega cross u plus f. We have the acceleration term, pressure gradient, the potential that includes centrifugal because of the rotation, Coriolis, and friction. So we are going to add friction here in a very simple way and show that when you have a wind, here is our constant pressure surface with pressure gradient across it. So there is a pressure gradient force going that way. We said when there is no friction, pressure gradient can be balanced by Coriolis to get geostrophic flow. But when you add friction in a normal situation, friction is always in the opposite direction to the flow. So if you're trying to move in this direction, friction is going to drag you back, right? So we show a little friction force. So now the balance is not just between the pressure gradient and Coriolis. You have to also include friction. So the winds or the currents become subgeostrophic. They're not in the geostrophic balance anymore, but you have to include the impact of friction. Okay, so the dotted line here is the vector sum of friction and Coriolis. Okay, that's now being balanced by pressure gradient force. So you can see that the velocity is still related to friction in a somewhat similar way to the Coriolis. Not very important, but in this simple situation, yes. Looking at the equation again, just keep looking at it so that you can just write it from memory and remember how we derived it. We still have to go back to our Rossby wave number being much smaller. So other than very special cases that we talked about, we still have Rossby wave number, Rossby number being very small. In that case, we had just the geostrophic flow with hydrostatic in the vertical. So if the F term is not small, then we put it back in. So we say Coriolis and pressure gradient are responding now to friction as an external force, and that was that. So flow here is called subgeostrophic. I'm repeating it because now we will write the velocity total as a geostrophic component plus an ageostrophic component. This is just a decomposition we are making under some assumptions. We won't go into the details, but this gives us some ideas on how friction affects the ageostrophic component. So geostrophy, we can assume, is still balanced by Coriolis and pressure gradient. So remembering our UG equals dP dx 1 over F rho, and U is dP dy minus dP dy, and V is dP dx, right? So if you remember it correctly and not like me. Nonetheless, you can take this expression that you can always use to derive. Put that into this equation, Fz cross U, a geostrophic. So the geostrophic component still balances this way, but the a geostrophic component can be made to balance the friction, right? So Fz cross U Ag, a geostrophic, can balance the friction, and the geostrophic component can balance the pressure gradient. Just a simple decomposition. So the ageostrophic component in this sense is always directed to the right of F in the northern hemisphere. Sounds parallel to the Coriolis we've been talking about. If Coriolis is to the right of F in the northern hemisphere as well. In the lab, this is created by creating a solid body rotation and then slowing down the tank. So at the bottom, the motion set by slowing down the tank is going to experience friction. So they put paper dots at the top and some dye at the bottom, and by changing the rotation speed, they can create high pressure or low pressure at the bottom. And you can see that the flow is spiraling in to the middle in this case, whereas it's spiraling out. Okay, so if you use your Coriolis and your cyclonic and anticyclonic flow, then you know that cyclonic flow is going to have a convergence, which means there has to be a vertical motion, whereas the anticyclonic flow is going to have a divergence, and the vertical flow is going to feed the divergence. Convergence, rising motion like we had in the atmosphere. Divergence, sinking motion like we had. So this is in the convection, and this is in the, let's say, subtropical gyre, where there is subsidence and divergence, right? So looking at in a simpler way, here you have low pressure center with high pressure around it. So you have counterclockwise or cyclonic flow converging in, whereas in the high pressure center with low pressure around, you have clockwise flow. You can easily see your Coriolis here. Flow going from high pressure to low pressure being tilted to the right, high pressure to low pressure being tilted to the right, here to the right, going out to the right, going out to the right, and so on. So you can always remember the fundamentals and derive this easily. So here is divergence, here is convergence. That is our subgeostrophic flow. Okay, it's very simplistic, but it gives you a very good sense of what friction does if hydrostatic balance and Rossby number being small are still essentially valid, so that the acceleration terms are still small. Remember, we don't have the du dt term here. We are still balancing Coriolis pressure gradient with friction, no acceleration, so it's still a kind of Rossby number, small Rossby number flow.